Thanks everyone for joining this webinar. This webinar is going to talk about a component of the Imubit process and product, which is a virtual dynamic simulation of a plant. Another way to call it is an AI dynamic process simulator. So this presentation was actually based on a presentation that we developed with the AFPM Subcommittee for Process Control. So we presented this presentation on August 17th, 2023 as a webinar. And what I've done is basically taking the same slides, but I'll be diving deeper into some of the questions that came up during that original webinar. But if you want to go check out the original, feel free to go to the AFPM website. You can search the title that's displayed on the slide here, or use the link, and you should be able to find that original webinar replay. Okay. If not, let's dive into it. During this webinar, we can talk about this concept of building this virtual simulation of a plant. So I'll first start out with a very high level introduction of who Imubit is. So if you haven't heard about Imubit, we developed an AI process optimization solution where the AI itself is directly controlling and optimizing the plant, specifically refineries. In addition to the final output of our process, we developed the process as well. And this process enables plant experts to leverage world-class AI, specifically a form of AI called reinforcement learning. So the base requirement for leveraging our solution and taking advantage of our process is you have to have a good understanding of the process that you're trying to optimize. But that's really it. And if you had to summarize our approach of developing these models in one bullet, it's that we take AI first, we leverage AI as much as we can, basically taking full advantage of your historical data, but then we're constantly constraining the model with first principles and embedding first principles at times throughout the model's development process. Okay, and we're going to dive a lot more deeper in that, and I'm going to show you exactly what a process expert defines versus what is automated and as part of the bigger automated solution. So today, over 50% of refiners have adopted our AI models, optimizing their most critical operating strategies. We have over 50 applications across these many different operating strategies at these plants, and some of these models have been engaged for over 5 years now. So, like I mentioned before, the final output of this development process is a pre-optimized AI model that comes on site for direct control of the plant. So how it works is the model sees a continuous state of the process conditions by looking at a historical rolling window of DCS data. Then it is also given the rules of the operating strategy, which plant experts can change in real time. So these are operating limits, economic parameters, maybe even quality targets. And the AI model has everything it needs to drive change directly through set points to the APC or the DCS layer on the scale of minutes continuously, maximizing whatever we define for it as its economic objective, and it's doing this all dynamically. Okay. So how this model is trained is with a special form of AI called reinforcement learning. So if you don't know reinforcement learning, here's a very quick explainer. So reinforcement learning is the act of training an algorithm to make decisions in a dynamic environment. So how it works is you have an algorithm, you have an environment. The algorithm then takes action on the environment. The environment changes due to the nature of this action. And then every time the algorithm makes another action, you give it a grade. And this is determined by a reward function. Okay. So the algorithm basically makes decisions over and over again, more than a human could ever do in their lifetime. It develops experience, or what's very similar to human-like intuition, as it continues to solve the problem many times. And eventually it gets to a point where it's able to maximize its reward and make the right decision every time, mastering the problem without simplifying the problem. Okay. So there's two requirements you need to fulfill in order to conduct reinforcement learning. You need to allow this algorithm to trial and error many times, more than any human could ever do in their lifetime, till it learns right from wrong. And where it does this trial and error needs to be a very accurate reflection of what you're trying to do in the real world. So this we commonly refer to as an accurate environment. So reinforcement learning has had a lot of media attention and applications of playing very complex games, board games. It's also had a lot of applications. It's a fundamental algorithm in self-driving cars. So you can, in those two examples, in a board game, the environment can be created because you have a fixed set of rules. You can create that game on a computer. You allow the algorithm to trial and error. And when it makes a mistake, it might lose the game and you just restart the game. In the self-driving car example, there wasn't data for people to start training models. So what did they do? They basically took cars in the real world, added a bunch of equipment, but they started allowing the algorithm to take action on the live car in the real world. And anytime the car made a mistake, there was a human safety driver in the car to give it feedback and to allow it to learn right from wrong. So you can imagine, you might be asking yourself, okay, so how is Imubit doing this at industrial processes? Because we can't afford to trial and error on the live plant, many, many times. So this is the fundamental problem that we solved at Imubit, where we allowed the reinforcement learning to take place offline first, to then bring a pre-optimized AI model on site for direct control of the plant. Okay, so how we develop this model is the following. We first start out with creating the accurate environment. And how we do that is we train a deep learning neural network on years of plant historical data to learn the true dynamics and process relationships that exist in your plant. Okay? And if you can effectively learn those relationships, what you essentially have now is a virtual dynamic simulation of your plant on the cloud. Now that you have this accurate environment, then you train another neural network through reinforcement learning, and you allow this blue neural network here to trial and error on the virtual plant hundreds of millions of times. Okay, and hundreds of millions of different scenarios is the equivalent of a human experiencing 10,000 years of different scenarios of a specific problem. And over these hundreds of millions of different simulations, you change the process state because now you have a simulator, so you can train over different process regimes. You also train across the entire optimization solution space. So, have it optimize and control when the operating limits are narrow, have it optimize and control across different economic parameters. And you allow this reinforcement learning model to solve across the entire solution space. And while doing so, it develops experience solving the problem. So once you validate, and this can only be done by a plant expert, and I'll show you some visuals and applications that allow plant experts to validate, what neural networks have learned. Once you validate that this reinforcement learning model is respecting the rules of the plant, you then bring just that model on site. And having seen the plant so many times offline across many different scenarios, it's ready to directly control and optimize the plant in the real world. Okay. And just to be very clear, this model that comes on site is installed on a very secure system that's on-prem. So the model that comes on site for direct control is on-prem, not from the cloud. But then once connected on-prem, it's able to directly control and write stack points to the DCS or APC layer. Okay. So for the rest of the presentation, I'm actually just going to go focus on, what it takes to actually develop this virtual simulation of the plant or the accurate environment. Okay. In future webinars, I'll dive deeper into the reinforcement learning model and how that's developed. There's also some content already on Imubit's website, so feel free to check that out as well. But now we're going to turn our focus to what we call the deep learning predictor, or the dynamic virtual simulation of your plant. And how this model is trained, like I mentioned before, is taking years of plant historical data and then training a deep learning neural network to learn the true process relationship of the plant. So, and like I touched on it before, and you're going to see it, as we walk through this development process, you're going to see that we take an AI-first approach, extract as much value from the plant data, but then embed first principles throughout the process. Okay. On a more technical level, what's actually happening when you're training the deep learning predictor is that the neural network is graded on how well it can predict dependent variables dynamically. Okay, and we'll touch a little bit more on that as we move through this presentation. So what are the advantages of this approach and using an AI-driven process model? One is you're specifying a very limited amount of things. You're specifying only what a plant expert needs to give you and what might be hard to see in the data. But then you allow the AI model to learn the rest of the relationships based on that given definition and the plant's data. And what is the output of that is you eventually can learn nonlinearity and dynamics that are hard to see or justify, at our level of understanding and looking at data. But these are the types of relationships that really exist in the plant. And like I mentioned before, to keep the model respecting what we know for sure are the laws of physics, you guide this model through its development process and in training with first principles. So at a very high level, what does this workflow look like? It starts off with a plant expert defining the data set and cleaning the data. And this basically sets up the model definition that you set for the deep learning neural network training. And through training, it's going to learn over hundreds of thousands of different process states because you have this multiple years of data. And then it becomes, okay, now that the model has learned these relationships, how do I evaluate it as a plant expert, what it's learned, and does it make sense, right? Does it actually line up with my understanding of first principles? So this is what I'm going to walk through each step in a lot more detail. And what I show you is exactly what a process expert does to develop this model. Okay. And the reason the process expert, and you're going to see the steps that look, very much in line with using first principles rather than going way into the data science, it's because we employed two specific forms of AI that help process experts walk through this process. And I'm going to highlight some of them. One is explainability, which is using different methods and techniques to explain to someone who understands the process, but not so much, the data science world, what these AI models have learned in really intuitive ways. And the other form of AI that we use is auto machine learning, which is automating a lot of the repetitive tasks that a data scientist might use and only exposing parameters of the neural network or models framework that a process expert could give, and then automating everything else in the background. Okay, and this really reduces the amount of specification that is needed to train one of these models while leveraging your plant's data to its full capability. Okay, so I'm going to touch throughout this at a higher level. You can check out some of the old AFPM presentations that we've done. We specifically did one on those two topics, and later this year, we'll be writing a white paper with them as well to dive deeper into explainability and AutoML. Okay. So the first step of this workflow, like I mentioned before, is to define the scope and design of the model. Okay. And how that is done is by truly understanding what is the operating strategy you're trying to solve. So this is heavily, if not all, first principles, right? So what you do is you align on the operating strategy that you're trying to solve, and you define the variables associated with that. So at this stage, when we're just developing the process model, we're defining what are the independent variables and what are the dependent variables. Eventually, when we move to train the reinforcement learning model, which is the controller and optimizer, the definitions change to manipulated, disturbance, and control variables. Okay. So when you look at your operating strategy and you define the variables, typically it's about 50 to 100 variables, somewhere in that range. Then you pull years of historical data that's sitting in your historian for those variables. And then it becomes a step of data set cleaning and creation. Okay. And the goal of data set cleaning and creation is to maximize your data set so you can have as much data for this model to learn from, while making sure that this data still reflects the reality of the plant operation. Okay, so both are very critical. So for example, you can see here, this is also done all by a process expert, because a process expert can actually contextualize what that data means. So you can see here, a process expert has cleaned out the data set. They removed an outage period over here. And when you remove an outage period for a single tag, it's going to have to delete that entire window because the model's not going to train if it's missing, one variable in this data set. But then oftentimes we see data compression. That's very common. So you can make some decisions on filling in that data set. Maybe you interpolate, maybe you hold the last value, maybe you append different data sources on top of each other, or you can even use first principle calculations, okay? But the goal here is you're maximizing the data set while, as a process expert, still making sure that the decisions you make on filling in data still make sense from, how the plant actually moves, okay? So you go through this process, you clean the data set, and now you have a model definition. What are the independent variables? What are the dependent variables? As well as a nice solid data set across multiple years. Okay. So you can imagine, even though you're looking at 50 to 100 tags, we're looking at data that's at a lot deeper resolution than we're used to. We created an application called the Model Builder that allows process experts to quickly look at data frequency or data compression, while also going back to a time series view to clean the data and add bad data rules. So that's what you're looking there on the left here. And then on the right are some of the techniques I mentioned before of employing AutoML and explainability methods. So before you spend a lot of time really developing the data set and then training the model, a process expert can run a quick data quality and signus analysis report, which uses a lot of techniques based on frequency domain analysis, for example, to identify, the level of noise and instrumentation signals. So that allows the expert to quickly see, what quality data they have at hand. There's also another function that allows the plant expert to double check their definitions. So we're expecting the plant expert to define, what is truly independent or dependent, what is causal. But at times you can check using, classic dependency analysis to see if an independent variable is truly an independent variable. Okay. And the last functionality that I'll mention here is, oftentimes you get in a position where, as a process expert in your first principle understanding, you may know that, okay, there's a list of 20 inputs that I could specify that could help me predict the dependent variable. But then you're looking for, on a statistical level, what is the fewest amount of inputs that give me the best prediction? So you can run through this input suggester, and it'll do just that using mutual information theorems and dependency to help identify, what are those statistically the best signals to use for a prediction. So now that you have your model definition and your clean data set, now you're ready for model training. And how it works is now you push your definition to the cloud. And now we're going to just look at what actually happens in training. Okay. But everything that shows so far is exactly what you would define for the model training, in addition to some other parameters such as a control window, which is the longest time to steady state relationship you would expect to see as part of your operating strategy, as well as the step size, which really is defined when you figure out the level of filtering and averaging you need on signals to keep the dynamics while removing instrumentation noise. But that's all you define for developing this deep learning predictor. So now when we look at training, what happens is, over the years of many data, we're going to break up those years of data into time to steady state windows, what we call the control window. So you can imagine for a conversion unit, it might be somewhere between 3 to 4 hours. And we break up our data set into many windows, and then we're going to feed these windows individually into the neural network as a single situation. So in a single situation, we give the neural network all the independent variable information it needs, which you can see here, just a single window of how the independent variables move dynamically in this period of time. We also give it a window of how the dependent variables move in that same amount of time, in that same window of time. And then we basically say, okay, neural network, we've given you everything you need to go ahead and make a dynamic prediction of the dependent variables, which is represented by this blue line right here, the DLP prediction. And now we can grade it because we have what actually happened in this historical window of time dynamically, which is this purple line. We pulled this from your historian as well. So now this delta between the prediction and what actually happened is called the prediction error. And our goal over the next hundreds of thousands of different situations that we have, because we're looking at such a big data set, is to try to get the neural network to predict exactly how the dependent variables move dynamically. Those predictions right on top of how the historical PV moved for the dependent variables. Okay. And if you can essentially do so, what you now have is a virtual simulation of the plant, right? Because now all you do is continue to give it where the independent variable is going, and it'll always tell you where the independent variable or where the dependent variables are going a historical window in the future. So training look just as we defined. You give it the model definition, you give it a clean data set, and I'm not going to touch on it too much, but like I mentioned before, here's another AutoML functionality of the process expert can actually define if they're very confident that there's a process gain that clearly exists based on first principle, they can actually define that as part of the model definition between an independent and dependent variable. They can also impose, physical relationships or equations on top of the model's definition. So when the neural network is training and looking through large volumes of data, we tell it, go find the true process relationships, but make sure you respect this equation as you do so. So now that we've trained the model and we've gotten the trained neural network back, our question becomes, okay, how do I know that what the model has learned actually aligns with how first principles works? What are the true physics of the plant? Now we move into our evaluation stage. So this is now showing some of the examples of the explainability methods we use to allow process experts to understand what the neural networks have learned. Okay. So a way of simplifying how the deep learning predictor learns, remember, its goal on a technical level is to learn how to predict dependent variables dynamically. But a way to simplify that for us to understand, as process experts, is to understand that it's learned thousands and thousands of steady state gains. Okay, so specifically what we do is we show on charts like this that between an independent and dependent variable over 10,000 gains, what are those gains that it's learned? Okay. In reality, the model is learning, hundreds of thousands of gains, but we basically simplify it to show, steady state gains on these distributions. I'm going to double click on this later, so I'm not going to go into too much detail right now. In addition, because it's a dynamic model, it also understands that independent and dependent variables have changing time dynamics. So the delay plots like this help process experts understand, what are those dynamics? When does the independent variables move take full effect on the dependent variable? And then the last plot, which is probably the most obvious, is you can actually visualize the dependent variables dynamic predictions and see how much error it has for different dependent variables. Okay, so not going to go into too much detail, but here is a really powerful application, which is a window into your dynamic simulation. Okay. And what you're seeing is exactly what a process expert can do, which is play around with their simulation and build confidence that this process model has learned the right process relationships. Okay. Or they can also dive deeper and learn more about their process and understand the relationships that maybe they knew in theory existed, but now they can actually see it in their plant data. So what we're looking at is a view of a single moment in time, a single window. Here, the blue are the neural network dynamic predictions on top of the yellow historical dependent variable movement. You can also see that our models learn a gain distribution between each independent and dependent variable. Okay, and you can double click on one of these gain distributions and dive deeper and learn the exact time that the model learned that steady state gain. And because this is a simulator, you can ramp and change different inputs and see the corresponding change on the dependent variable dynamically. And this application works both on historical data and on real-time data. So you can constantly play around with your plant simulation and learn more about your plant. Okay. So I want to move into like a smaller case study where we show, building a deep learning neural network, the deep learning predictor on a refinery hydrocracker. Okay. So I got a simpler problem here just for this case study. So you can see here's plant data like from a historian, and we're plotting total feed versus diesel product flow here. And this is a two-stage hydrocracker, so you can see there's a first stage wabbit and a second stage wabbit against that diesel product flow. And we can clearly see that there's a linear relationship between total feed and diesel product flow. So we don't need, any type of special modeling to model that specific relationship. But what's hard to see is any type of clear relationship between the first and second stage wabbit against the diesel product flow. So if we kind of aggregate first and second stage wabbit, that's total conversion of the hydrocracker. If you look at a hydrocracker textbook, you'll see a plot like this, right? So theory basically says, as we start to increase conversion, so conversion is on the x-axis, on the y-axis is yield, and let's just focus on this diesel curve right here in green. So as we start to increase conversion, there's a point where I start to actually make more diesel, right? My diesel yield goes up as I increase conversion. So I have a positive steady state gain. But at some point, as I continue to increase conversion, I actually see an inflection in my diesel make, and I start to lose diesel yield. So I have a negative gain between conversion and diesel. So this is commonly referred to as overcracking, right? So you can see theory on a hydrocracker tells you that you do have nonlinear process relationships between conversion and diesel, and you also have nonlinear process relationships with your other distillates as well. Okay. So it starts to become really important, on a simplified level, if you're just trying to make more hydrocrack or more diesel in your hydrocracker, it really becomes important to understand this nonlinearity. So when we train the deep learning predictor on hydrocracker plant data, right, we see exactly what theory tells us. So the model shows us when we look at the gain distribution, so gains are on the x-axis here. Y are the number of instances across 10,000 different situations that we see the steady state gain. So it's the frequency. So you can see a deep learning predictor trained on hydrocracker data learns exactly what theory tells us, that there's positive gains represented in blue, and then there's negative gains represented in red. And not only has it learned that the sign changes, but it also learns that the magnitude changes, representing the steepness change of the curve. And like we saw before, our process model is not just learning, a nonlinear gain for one independent dependent variable. It's learning it across the entire matrix, if you want to call it, of independent dependent variables. And if we see something that's, if something is truly linear, you'll see that this gain distribution on the sign side is very narrow to represent a linear relationship. But it becomes really powerful when you can imagine a hydrocracker. If you really want to optimize a hydrocracker, you have to understand the nonlinearity between conversion and all the distillates. And that's exactly what you see when you train a deep learning predictor on the data. And it's key here is that we're not training on, 40 or 50 data points, because that's not going to be significant enough to understand the process. In addition, we're not training on steady state process data. We're training on true dynamic process data. So when we actually train the deep learning predictor, we're training on, hundreds of thousands of different process states. And we train it in a non-sequential way. So the model is learning truly new situations and constantly improving its dynamic predictions. And that's how you get the power of truly understanding the nonlinearity in your process. Because these are types of things that are very hard to specify as a process expert using first principles. I'll show you another example, which is also very powerful, of the benefits of using, a deep learning neural network on a lot of plant data. And this one's on a FCC, so a fluidized catalytic cracker. And very similar approach, for this customer, they wanted to understand how their riser outlet temperature, so the equivalent of conversion on FCC, impacts their yields and their other control variables. So how you set up the problem is like exactly what we showed before. Process expert would define the independent variables. In this case, it would be riser outlet temperature. And the dependent variables are all the yields and the critical constraints in an FCC. So, compressor outlet suction pressure. For the wet gas compressor, maybe it's the slide valve DPs, and for sure all the product yields, so cat gas, diesel, etc. Okay, so I'll start at the bottom here. So how this model was trained originally was we gave it 3 years of plant data, okay, and then because we trained the model and then we wanted to add more new data based on recent plant performance, there was a window in our data set, so a gap, and then we added 3 more new months of data. Okay. And when we looked at the gain distributions that the model had learned, we saw something very interesting. We saw that, you can see here, so here's slurry, here's PPs, here's cat gas. You can see on some of these gain distributions, we see a bimodal distribution. So what that means is we see a big peak and then we see a small peak, right? So we see a big peak here on this cat gas and then a small peak, right? So we found this very interesting. And, at first we didn't really understand why we saw this, but when we dove deeper and we used some of the functionality in that application I showed before, we were able to see that there was a very specific time period that was associated with the small peak, and that was actually the new data. So the old data was shown in the bigger peak. Okay. So we went back to the customer and we asked them, okay, so why do we see this bimodal distribution? And what they told us was, hey, you know what we didn't tell you was we actually we started introducing new higher conversion FCC catalysts right in the gap where you didn't have any data. So the new data set, the 3 months of data, represents the higher activity catalyst with more surface area. And the old data set represents no introduction of this catalyst, so a lot lower activity catalysts circulating the FCC. So you can see what we basically are showing here is that the DLP just trained on riser outlet temperature against all the yields has learned inherently, it's baked in the data that the catalyst activity has changed, right? And we didn't explicitly define it because there's no variable called catalyst activity that we can continuously get. So what it's learned is that, hey, I don't know why, but in the recent times, my ROT now gives me higher cat gas octane, lower dry gas, higher cat gas production, higher PPs, lower slurry. Okay, so you can imagine in real time now, as the customer is running with this higher activity catalyst, the AI model in closed loop is going to look at the current state of the process, reflect back on where it saw this state in its historical training, and now it's going to, in a simplified way, pick the gains in the smaller peak because that's the type of situation it's seeing on site. So what does that mean in terms of when you're actually controlling and optimizing? If you didn't understand the impact of the new catalyst, you might actually think that, hey, my cat gas octane, my cat gas is going to be a lot lower if I use riser outlet temperature. So you might preferentially think that the optimal is feed over riser in a simplified way. But in reality, a model like this can actually understand in real time that, hey, right now is the time to use more conversion rather than feed and favor conversion over feed at the dynamic level. Okay. So this starts to become very critical when you're trying to optimize the plant, is modeling these true plant relationships, which you can do when you effectively use, a large amount of your true plant data. So the last slide that I want to talk about is, what is the typical timeline to developing this deep learning predictor? And you can see that for the most part here, it's close to about 1 to 2 months, but you can see that a large majority of time is spent defining the problem and aligning on that, which is exclusively first principles. Then it becomes a stage of cleaning that data set, which uses a lot of first principles again. The actual training time, the computation of building this is really short, right? Because you're doing it on the cloud with modern day computing. So that's about like 30 minutes to call it a couple hours per iteration. But then the other large part of the time sink that it takes to develop this model is evaluating it, right? How do I build confidence and make sure that what this model has learned aligns with my first principle of understanding? And you can imagine if you find something wrong in evaluation, you're going to go back through this, workflow maybe one or a couple times. Yeah. But keep in mind that the original intention of this process model was to build a process model that was going to be an accurate reflection of the plant. So we build this accurate environment to then train the reinforcement learning model, which is here on that gray workflow, the deep learning controller. But imagine if you just want to build a quick simulator to understand your process, or maybe do a quick debottlenecking, simulation, this timeline could be a lot shorter. So thank you for your time. Hope you learned a lot more about Imubit's process, the approach that plant experts can take, leveraging AI, getting the most value out of your data while using first principles all throughout. And then look forward to future webinars where we talk about how we go past this accurate environment, the deep learning predictor, to create and leverage the truly powerful form of AI called reinforcement learning that is used for the controller and optimizer that goes on site. Thank you.